Hello, everyone, ladies and gentlemen. This is Alice. I'm really glad to meet you online for I Can X Talk, as this is every Friday program. We connect world and universe by the science talks. So this is Alice from Peking University, and it's warm greetings here. And it's also the best weather, best season here. So no matter where you are, what time you are, welcome to I Can X. This September, actually, we have a big group because this we have 5 weeks. We have 6 wonderful speakers. We have Zhong Li in the first week. Then we have Nicholas Peppers next week. We have 2 young scientists. In the third week, we have Annie Roberts from Australia last week. And this week is the last week of September. The big name Brad Nielsen is here to deliver a wonderful talk. So this was I Can X tradition. Every week we have a major speakers and we have a panelist for the discussions. We have a challenger, young scientist, to ask the most sharp questions. So this was today's team. So our speakers is Professor Brad Nielsen. Brad Nielsen, actually, I don't need to give a very long introduction because everyone know him. If you follow about the micro nano robots or this artificial intelligence work, you must know his name. His name was something like in this area for I think more than 20 or 30 years. And he's not only deliver a lot of nice science papers, he also put his technology into the commercialize. Yeah, it was have 3 companies like that, startup companies, and products get on the market. And Brad Nielsen also, have a very colorful life, have a rich experience. We can discuss and panel discussion. Now, without further ado, let's welcome Professor Nielsen to deliver his talk for the micro nano robots, please. Yeah, Brad, please.
Well, thanks, Alice. It's a pleasure to be here. Thank you very much for the invitation. And I will share my screen now. Let's see. Hopefully it comes across good there. And yeah, I'm speaking to you today from Zürich, Switzerland, where I've been 20. Actually, tomorrow will be my 20-year anniversary here. So October 1st, 2002 is when I came. So and what I want to talk today is about the robotics part of micro and nano robots. As Alice said, I've been working in micro and nano robots since I became an assistant professor in 1995. And when I came to Zurich, I started thinking about how to make small micro and nano robots themselves. And so I want to talk about that, but I'm fundamentally, I'm a robotics person. I'm a mechanical engineer. I studied robotics for my PhD at Carnegie Mellon. I've worked in industrial robots, visual servoing, force control, all the classic areas of the field. And it was when I became an assistant professor, I started thinking about micro and nano technologies and how we can bring those in. But still, a lot of what we do it has robotics in it. So I want to talk about that today. Before I get started, I just want some disclosures. I've got a couple of companies. Alice mentioned Magnobotics and Nanoflex. You'll see some of that work here, and I just want everybody to be aware of that. So I'm involved there. And I like to start by thanking my team. I have a fantastic team. I've had a lot of really great people through over the years. We have about 45 people in the group right now, and that means a great administrative staff, engineers, software engineers. I've got a co-director, Professor Salvador Pani, who's a chemist, scientists, postdocs, PhDs with a broad experience. Because I think micro and nano robotics requires a broad experience. Like all of our technologies, you want to bring a lot of different things together. And as I've worked in this over the years, the real application area, the main application I should say, we see is medical robotics. And so I want to talk a little bit at first about medical robotics and that part of it. And this is a advertisement I downloaded off the internet many years ago. And I think it's really interesting because it's from a hospital in Miami, Florida. And they photoshopped a robot arm onto a surgeon. And the advertisement says, 1 part surgeon, 1 part machine, both parts amazing. Robot surgery now at Palmetto General Hospital. And they're advertising that you should come get your surgery done there because there's going to be robots helping the doctors do that. I think that's quite illuminating. And this is several years old. Of course, they're talking about the Da Vinci system from Intuitive Surgical. quite successful system that's done over 10 million procedures, well over 5,000 of these systems around the world, several right here in Zurich that are performing surgeries every day. And it's encouraged a lot of people to get into this space, a lot of companies. Intuitive Surgical has been very successful financially and therapeutically. And so there's a lot of ideas people have trying to get in over the last 20 years or so. But there's two companies I want to trends in the field, and I think one is from Auris Health and the other is from Intuitive Surgical itself. And what they've both come out with in the last few years are very small endoluminal devices. These are endoscopes that are around 3 or 4 millimeters in diameter. This is Auris Health. They were bought a few years ago by Johnson & Johnson for $3.5 billion, a little bit more than that. And Intuitive Surgical is bringing their ion system to market. And what you see is the trends in the field are smaller and smaller endoluminal devices that are guided along more tortuous paths. They're looking here at going into the lungs to look for lung cancer, to try to diagnose it more quickly, get biopsies and get out. And I think that's interesting, but there is a limit to how small they can make these devices. And that's where my research comes in and where the microrobotics community comes in, because what you see is kind of a convergence of the medical robotics, large places, and then the micro and nano robotics people, because we can only make these devices so small. And eventually these catheters are going to get close, but we're still going to want to release devices that are going to be able to bring our drugs and our therapies more closer to the disease. If you're treating say brain cancer, if you're treating stroke or some of these diseases. And so it's really kind of the top down, which is the medical robotics meeting the bottom up from the micro and nano robotics. And micro robotics, of course, has been a topic for years and years. I would say about 20 years, where people have really started focusing on making small machines. This is an example. This is a paper we recently published with one of Alice's colleagues. The first author here is Chanyan Wang, an assistant professor at PKU. Hongwei Gu, who's now doing a postdoc with a physicist in Germany, one of my deep thinkers. And we were just kind of looking at where the field has gone over the last 15 years or so. And we started in 2007 with our first swimming micro robots, and we just continually tried to make them more complex, adding functionality, programmability, reconfigurability. I'm going to talk a little bit about storing data, the lessons we know from the disk drive industry we can actually use in our robots, and where we're heading are just more and more intelligent, integrated micro machines. I think work that's coming out of labs like John Rogers with dissolvable electronics and flexible electronics, and some of these things are really coming together in very interesting ways. And we see these trends in the field. Now, if you're a robotics guy, a mechanical engineer, you look at this and you say, well, it's really a materials and fabrication problem primarily. And I certainly will tell you, yes, it is. Materials and fabrication are absolutely key to this. We spend a lot of time on this. My co-director here at ETH Zurich is Salvador Pani, a chemist. And we think these materials, issues are a big part of what we do here, of course. We like to use magnetic fields to make these things move. So we spend a lot of time on developing better ways of fabrication with magnetic materials and with biocompatible materials. What are they going to carry? The therapeutic cargo, the drugs, the biocompatibility, biodegradability thing. If these devices are going to be in your body, preferably you would like them just to sort of dissolve after they're done. You don't want to have to retrieve them. These put a lot of constraints, of course, on what you can do. We can all make cool looking robots that are hopping around and, get in the news and the science press picks them up. But when you really focus on the materials that are really going to work and that are really going to make it across the regulatory pathways, the problem becomes much harder. And it sounds less sexy probably in a way, but I think it's really what's going to make the impact. We also have to think about things like contrast agents so that they can be seen in the body, like through X-rays or MR. Can they adapt to their environment and show some kinds of intelligence? If they're small, we're probably going to need a lot of them. We have to understand how to make many move together. And then we have to be able to integrate these all with the imaging, tracking where they're going, and with the magnetic navigation systems. But one of the very first problems we thought about when we entered this field back in probably 2003 was when I first started thinking that this might be something worth pursuing, was how are you going to make these things move? How are you going to power them, and how are you going to actuate them? We know that power storage does not scale well. It's a volumetric property. And we quickly realized that magnetic fields were had a lot of benefits. They're safe. We know they're how safe they are for humans, and we have a good sense of that. They're long-range forces that can be projected through the human body. And there's a lot of different ways we can generate. There's a lot of options in how we generate fields. It's interesting. But other people have looked at other approaches, for instance, looking at catalytic motors that use things like hydrogen peroxide as a fuel, or hydrazine, or these kinds of materials. More recently, folks have been looking at photocatalytic devices that are basically, gathering photons and using those to create hydrogen ions, and as from water, and as those ions are moving past the device, they propel it. But another area that I think is exciting, and that Daniel Ahmed out of our lab, and who's now an assistant professor at ETH, has been working on, has been ultrasound and using acoustics to drive these. And that's another area we understand the safety concern. We understand how safe those are for the human body. But I'm going to spend most of my time talking about magnetics today, because that's what we think is probably nearest the clinical application, and what a lot of our research has been over the years. So I want to start with some just basic physics on magnetic actuation. There's two things we need to know: how to generate a torque on a magnetic object, and how to generate a force on that object. Okay, so if we've got an object with a magnetization, so it's something like iron or cobalt or neodymium iron boron, it's going to have a magnetization vector. The torque is going to be a function of the volume of that device, and then it's going to react to a magnetic field B. So if I put that device in there, it's going to try to align its dipole with that field like a compass needle does. That's pretty straightforward. Forces are a little bit more of an issue because they're attracted by the gradient of that. So if I have my micro robot, or my little magnet, who is aligned with the fields, it's going to want to go in the direction of the positive gradient to where it's getting stronger. So one of the So making these devices, the micro robot here that I'm showing, in these two here, is a lot of the materials problem, a lot of what my materials fabrication group does. But another big part of what we're interested in is, how do we generate these fields, and how do we generate these field gradients to make them move through the body? And I think that's a very interesting robotic problem. There's basically two fundamental ways that you can generate a magnetic field. One of them is with a permanent magnet, a bar magnet, like neodymium iron boron is their favorite one. It's because it's the strongest. It was reported out of Japan and the US simultaneously back in the very early 80s. And it's the best magnet we've got, permanent magnet. And of course, as we all know, magnets are dipoles, and we've got our flux lines going from north to south. And so what we can do is we can use that magnet, which has its constant field that doesn't change. We can put it on the end of a robot arm, and we can start moving it around and changing the fields and the gradients by rotating and translating that. And this is what Pietro Valdestri does, and he reported a few years ago in Nature Machine Intelligence some in vitro experiments for colonoscopies and guiding colonoscopes inside of the large intestine. Zhanwei Zhao at MIT has also done this. He recently had a paper in Science Robotics where they put a permanent magnet on the end of a robot arm and then move that robot arm to guide catheters in the brain. And Zhanwei's done some interesting work, and Yunho Kim, his PhD, his postdoc now, has really done some really interesting things there. Now, I think one of the things you'll notice is you've got this permanent magnet, and it has to move around the patient. And there's another way we can generate electromagnetic fields, as you all know, and that is with an electromagnet. So we start with, usually we'll have some kind of a core that's a soft magnetic material, something like iron typically, or iron cobalt is also got some nicer properties. And then we put, of course, a current carrying wire, copper, around it. And as we put a current through there, we generate this field like a permanent magnet. But the advantage is, as we put more current in it, of course, we get stronger fields. And we can also reverse the polarity just by simply reversing the current. So all of a sudden, we can keep our electromagnet stationary, and we have a lot more degrees of freedom, a lot more control over it. And we can also turn it off. And you cannot turn off permanent magnets, of course. And that's also one of the problems with permanent magnets. So we've been thinking about electromagnets for quite some time, and we spent a lot of time in my group building electromagnets. The whole problem with electromagnets is you want to put as much current in them as you can without melting them. So it really becomes a heat transfer problem. It becomes one of thermodynamics. And so we spent a lot of time on how we wind these, how we cool them. And one of our key findings over the years has been a patent on a permeable winding technique that allows us to cool these very, very rapidly and efficiently, which can increase the power density by a factor of 5 over traditional electromagnets. So this is a piece of our IP that is important and licensed and is used to produce high power density electromagnets. So now I can take that one electromagnet that I'm showing you here, and I can combine it with several other electromagnets. When we started looking at this back in the around 2008, 2009, when Jake Abbott, who's now at Utah, was with me, we started thinking, how are we going to describe this as a robotic problem? And so we started thinking about robot manipulators. If you've ever taken an introduction to robotics class, you learn something about robot kinematics. And you've got, for instance, a typical robot arm has 6 joints. And there's a very clear way in robotics that you handle the mathematics of how you map the velocities of each of these 6 joints in this manipulator into the end effector motion that moves it. And that's how robots in factories pick things up. So this is through the manipulator Jacobian. We put joint velocities into end effector motion. And we realize that we can look at our electromagnet systems exactly the same way. So we look at the input as coil currents, and the output becomes the magnetic fields and field gradients. And so now we've got all the we've got over 50 years of research in robot control and design that we can come to bear on the problem. So controlling electromagnetic complex fields and field gradients, to me, is the identical problem of controlling a robot manipulator. And this is some of the mathematics we did with Jake Abbott over 10 years ago now, where we just took an n number of electromagnets, in this case 8. So we have an input of 8 currents from each of those. They're put through this mapping, which contains the magnetization of the robot, the micro robot we're controlling, so its magnetic properties, and that's a function of its material, of course, as well as its position in this workspace. And that then can give us the torques and forces that we can generate on our device to make it move. And this looks exactly like what we call the manipulator Jacobian, that's been well known in the robotics community for decades and decades. And that helps us in 2 things. It helps us optimize the design of our robots, and it also helps us control our robots and analyze their performance. This again is something an idea we patented that's been licensed and it produces a little bit of revenue. So, but one of the questions, one of the things that's important about robots is the workspace. What can you manipulate? Where can you reach? How much force can you generate? And so we started thinking about, how do you design a robot workspace? How do you think about the workspace of an electromagnetic navigation system? And so we think of, if I think of a 2-coil system where I've got a coil I1 that goes into one of them and a current I2 in the other, there's going to be bounds on that. We know that if we put too much, it's going to exceed our power supply requirements or melt our system. And then that's going to translate through this actuation matrix into the available fields that we can generate in there. And then we can think about the task we want to do with our micro robot. And we can think, what fields do we need to generate to achieve our task, right? And so then we can look at where we fall in that space. And if we're out of that space, then we're in trouble, right? So so we think of our feasible and our infeasible regions. And so this maps directly into robotic kinematics and all those things. And I'm not going to spend a lot of time on this, but I get excited about it. So I got to spend a little bit of time. And so here's our 2-magnet system. This is just a planar system. We always start with a plane. Here's our micro robot. And then these are the complex fields we generate. The currents generate into a task. And then this is where we need to be in order to achieve our task, because these are our feasible positions. And that space, this space D, is not always clear how it's generated. And there's a lot of different computational ways we can create that and look at that. It can have voids in it. It's not necessarily a homogeneous space. In fact, it's not homogeneous at all. And it may have separate regions in it. So these are all interesting mathematical problems, and robotics people, the deep mathematicians and love these kinds of problems. So we can look at our Navion. That's one of this is what I'm going to start talking about, but our 3-coil system I'm talking about. And we can start analyzing that as we put, say, 40 amps into it and we want to create 6 millitesla fields. We can start thinking about where we're getting that. We can start thinking about the workspace. Where is this going to be feasible? How are we going to generate the kinds of fields we need, and what errors might there be in those fields? So a lot of the folks in the micro nano robotics community are just trying to make micro nano robots. What we're thinking about, or at least part of my group is thinking about, is how are we going to generate the signals to actually make these things move? And so we're going back to robotics to do that. One of the things that's important is to create evaluation metrics, and there really aren't clear metrics on this for magnetic micro nano robots, but there is for robot arms and robot manipulators. And there's things we call manipulability index. Sunio Yoshikawa back in the mid 80s developed something called manipulability and defined that mathematically. And so we think about these kinds of things, but we also developed a new metric where we've got some D, which represents the task we need, and A represents the available fields and gradients we have, and then we can just define some distance. D is what's the closest distance D is from A, and then that can tell us how good our robot, our magnetic manipulation system, our electromagnetic navigation system is at doing the kinds of tasks that we need to do. And it looks simple, but actually the math explodes and becomes quite interesting very, very quickly as you start looking at these things. For instance, I mentioned before the Octomag. We built a large animal system with 8 electromagnets. And we built that back around 2009, 2010, and we did not understand why we needed 8. We just did numerical simulations, and we could tell when we got to 8 electromagnets, it gave me the ability to control a micro robot with 5 degrees of freedom. And when I say 5 degrees of freedom, I mean it could move it. We could control it X, Y, and Z, and we could point it in 2 directions. I just can't get this very easily. It's not. You have to play some tricks to get this axis to go. We kept realizing 8. We didn't know why 8 exactly, but but our numerical simulations gave us this. So when Andrew Petruska was doing his postdoc with me, he sat down and went through all the math and the mathematical proofs, and we were able to put a minimum bound and really understand, there is obviously a mathematical reason, and we can actually prove that the minimum number you need is 8 to move something with these 5 degrees of freedom. And as we reduce the need of the task to fewer degrees of freedom, we can reduce those electromagnets over time. So there's a lot of robotics, a lot of real fundamental robotic math and geometry, the kinematics that can go into this. And I think that's quite interesting. So over the years, we built a lot of electromagnetic navigation systems. Our first one, the Octomag, came out in 2009. It's great for small animal studies and how we can do these things in small animals. We built smaller ones, the Nanomag and Minimag, to go under microscopes so we can play with cells and manipulate them with magnetic particles and wires. We built the bigger one. I just showed you the Cardiomag, the CMag, we call it, for large animal studies. We've done a large, I'll talk about in a bit. And we've even built a clinical system called the Aeon Focus that's in a hospital here in Zurich and has done patients. When that came out in 2015 and started working with hospitals, we realized right away, a big, and this thing weighs 7 tons when we put it together. 7 tons is a lot, and it requires a lot of infrastructure changes to a hospital, and that's a hard sell to a hospital. So what we did was we started thinking, can we reduce the size of these? And so we started making smaller and smaller ones, and recently what we've created is this one I've referred to now called the Navion, a system that's all self-contained, has all the power and cooling and everything in it. And these systems over the years, then, and we've learned how we can control these micro robots. This is just 3 electromagnets, so we can control only limited motion. But if we have an 8 electromagnet system, we can very precisely control these micro robots with these 5 degrees of freedom. And what you'll see in this plot is you'll see our micro robot is always aligned. Its easy axis is always aligned with the vector of the field. That is the direction of the magnitude of the field, and it's always heading in a lot to the red direction, which indicates the stronger gradient, the stronger field in that direction. So it gives us ability to do that. The other thing we realized as we were working with doctors was it's a lot easier if you can integrate into their surgical workflow, if you can work with them the way they're operating. And doctors don't want to put devices and just have them swim around in you, but they are willing to put catheters into your body and endoscopes. And if we magnetize the tip of those catheters what we can do then is we can start to move those catheters with the same kind of math and the same kind of analysis that we used before. And that was how we decided to build some of the larger systems. This is our Aeon Focus, and this is the control unit that the doctor uses, like a joystick, the catheter, the device. Here it is in the hospital. You'll notice one thing about it is it's got these coils and it comes apart. So you can then get the patient ready and then bring it together. The doctor goes back to his control room or her control room and starts doing the procedure and moving this catheter, in this case, doing an ablation procedure to treat heart arrhythmias. Here is one of the days where Dr. Duru was treating a female patient. She was suffering from a heart arrhythmia. She was awake during the procedure, and he's sitting back here. He says, I can drink a cup of coffee while I do surgery. I've never seen him do it, but he says he can. And he's controlling this remotely while the catheter is being guided into the beating heart of the patient. We learned a lot from this. We learned that we need to have learn a lot more about how to design catheters. So not just micro robots, but the catheters themselves were obviously an important part. We took over that. Also, we realized at this time that if we want to get into hospitals, we really have to figure out a way to get in easier, make it easier for hospitals to adapt our system to it. And so we started thinking a lot about magnetic navigation systems and the workflow. So there's the leader in magnetic navigation systems is a company called Stereotaxis out of St. Louis, Missouri, and they have a system. Their new system is called the Genesis. This is it. It has 290 kilogram permanent magnets. So these are big permanent magnets with super strong fields. You cannot turn them off. You have to, it takes a few weeks to modify the operating room to bring this in. And then you never turn these things off. So you have to use, you can only use the operating room for this particular procedure. They do cardiac ablation procedures as well. But there's a lot of doctors, there's over 100 systems out there that people are using in parts of the world because they like that ability to control these catheters very precisely. Now, the Aeon Focus was more of a hybrid system because it could come apart and we could turn it off because of electromagnets. So that was a little easier for hospitals to take, but still, when you have a 7.5 ton system, you still got some issues. You need to reinforce the floor. You often need a brand new operating room, and that takes years for hospitals to decide to do that kind of thing. That's when we decided we wanted mobile systems. We wanted to try to figure out, can I make a mobile magnetic navigation system that I can easily wheel in and out of any operating room without much problems? And so that's what we've been spending some time on. We developed something, we call it the Navion for remote magnetic navigation system. It consists of 4 main components. So there's the system that generates the fields that I showed you before. It has an advancer. So this is a mechanical device that moves the catheter or endoscope back and forth. It just pushes it. And then the catheter endoscope has a magnet on the tip and it's steered. And then there's the software underlying that controls all this. And in our research lab, we do this all with the robot operating system, ROS, which just about all research robots in the world use. It's a very robotic system built on robotic software, robotic kinematics. There's a lot of advantages, I think, to the Navion over what current technologies are out there. It's, first of all, greatly simplifies installation in operating room. We've had it up here, just up the hill here in the women's hospital. We've had it in the animal hospital nearby. We've had it across the street for a demo in our for a scientific event. We've taken it up to the Netherlands and tested it with Philips. There's one right now on its way, as I speak, on its way to Hong Kong to go into the Hong Kong Science and Technology Park to do some experiments. So it's easily installed, it's easily shipped. All it needs is water to cool it and a special power plug. So that's super, and that helps in getting people interested in using it. The other thing I love about this system is it's easily movable when you're not using it. You can just wheel it out of the operating room. And when you are using it, it's not moving at all. And unlike permanent magnets, which have to move around the patient, which also has a risk of collision with patients, doctors, and the people working there. The other thing that's important is you turn it off and you don't have magnetic fields, so you don't have to worry about that. With the Stereotaxis system, that can't be installed within 30 or 40 meters of a magnetic resonance imaging machine. That's quite a constraint in a hospital because it will interfere with the fields that an MRI needs. We don't need room shielding, so the room is minimal impact. We've had it with angiography systems, systems that can, for seeing blood vessels and cardiac vessels in your body. And the other thing that, especially as a mechanical engineer, as a robotics guy, is that the dynamics are much faster because I'm just controlling the currents. I'm not having to control the mechanical motion of an arm. Mechanical bandwidths of arms are quite limited to less than 10 hertz typically, usually much less than that. And we can get dynamics in excess of 50 hertz, which I think is a lot of, which gives us a lot of possibilities. So I think there's a lot of selling points, but permanent magnet people will tell you, and they are right, their permanent magnets are stronger, can generate stronger field, but we are getting close to what their capabilities are with our special patented technology for removing the heat from these coils. We've also spent a lot of time on catheter technologies, developing catheters that can move across open spaces, developing catheters that, and also I should say filing patents on these too, that can change their stiffness. They can be either stiff or soft depending on what procedure you're doing. And also making catheters that are highly dexterous, that can tie themselves in knots, and that can be manipulated in paths that current catheters are simply not capable of doing. So what are we going to do with this technology? I talked about cardiac ablation before, but what we've been focusing on more lately is stroke. It turns out stroke is the leading cause of death in the world. The most common stroke, 87% of strokes, are ischemic strokes. Those are from blood clots that get stuck in the brain. I was just telling Alice, I was just down in Botswana last week, working in a remote area, trying to figure out if we can use our systems in remote clinics so that we can treat this disease. Now, there are different ways to treat this blockage. One way is to put a drug in to dissolve it, but there's a lot of contraindications to that. There are a lot of bad side effects. A number of patients can't handle that, and if you wait too long, it's not going to do any use anyway. So what's been discovered in the more recent years is the mechanical thrombectomies are actually quite effective at removing these. And a mechanical thrombectomy typically means that you put a catheter often in the femoral artery, you snake it all the way up the aorta, across the aortic arch into the brain, and then you either suck it out, you aspirate it, or you have a little net-like cage that grabs it, what we call a stent retriever that pulls it out. And what is really important when you suffer a stroke is time. Time is brain. And the longer you wait to get treated after a stroke, the more brain cells that are going to be dying, the more you're going to have disability when you're done. And so speed is everything. Getting to a stroke center, and most hospitals are not stroke centers, you got to go to a special place, is quite important. And it also takes a long time to do the procedure. The way it's currently done now is you've got a surgeon standing there, here it's an interventional neuroradiologist, putting a catheter that often has a little bent tip on it into the femoral artery typically, and then through X-ray guidance, snaking it up through the body. So they're controlling it at the proximal end and watching it at the distal end. And if you're a roboticist, this is the non-collocation problem. And that is one of the benefits of our system as well, is that if we are able actually to control the tip of the catheter, not just see it, but actually exert the forces magnetically on it. So this gives, we think, surgeons the ability to more rapidly perform their therapies. The other thing is, if you go to a cath lab where they're doing this, they'll often have a whole cabinet full of catheters with different bends in them. Because what they're doing is they're pushing this catheter up and they're twisting it and trying to snake it into the different branches of the arteries. And sometimes they get the wrong bend. They have to take it out and start all over again. And we don't need to do that because our catheter can be bent by magnetic fields. And so this is down in my lab downstairs here. Here's a fluoroscope. Here's our Navion. And this is a model of a human vascular system. We're controlling it with a game controller now, but we have other interfaces. This is a fluoroscope image. This is a phantom 3D printed aortic arch, and you'll see the user here. In this case, one of the student researchers guiding it up one of the arteries deep in the brain, and able to retract it then through the mechanical advancer pushing it and pulling it, choosing which vein to go in, not having to rotate it, not having. The other thing that's important is the person operating doesn't have to stand next to the patient and get irradiated with these harmful X-rays. You can easily select which branch to go up. Doesn't worry about having to find another catheter that's maybe more suited for that particular branch. And then basically just trying to navigate as they want. Here's a little demo of one of our magnetic devices versus the commercial way it's done. So this is all, the tip is bent, and you'll see what's going on here with the commercial device is it's just being pushed up, rotated, and kind of bent into place. And you can see that just the dexterity. This shows the magnetic field and how it's pointing in the workspace in this way. And here is some of the different ways. So you can see it looks like it should be much easier to do, but there's still clinical trials that need to be done on all this. But here's an example of an interventional neuroradiologist. This is Dr. Philip Gruber, who's at the Canton Spital, the Canton Hospital in Aarau. He does these radiologies procedures all day. Here's our Navion. Here's the X-ray system. This is, in this case, a large animal. It's a pig. And here he is guiding, in this case, a 2 French, 700 micron diameter guide wire deep into the brain of this pig, and he's able to select whichever branch he wants to go in quite easily. Doesn't have to pull it out, doesn't have to twist it, and he could actually be doing this remotely. And in fact, we've had this system remotely controlled from doctors in China, in Australia, in the US, and I was just down in Botswana last week, and we were controlling it from the Botswana International University of Science and Technology, and all over Europe. So people can dial in and control these catheters remotely without actually having to go to the cath lab. One of the things that Dr. Gruber was excited about when he did this was that this one part here, you see this little circle, has a very sharp bend in it. He wants to navigate from the maxillary artery to the caudal auricular artery, and that's a typical bend. He says, I can't do that with my current tools. But what he was able to show with our system was that he could go down any of these branches as he chose using our magnetic navigation system. This is something he just said, I just don't know how I would do this with our current technology. So we're quite excited. And here, I think he's about ready to make that sharp bend. It's a little tricky. This is his first time using it in an animal. So he's spent 7 years learning how to do this in humans, and this is his first time using this new system, and was able to very intuitively guide it and get it into the kinds of arteries that he needed it to go into. So there's a lot going on in this system. This is our Navion. And I talked about the fields, but actually the fields are pretty complicated. And I think this is one of the fun parts of it, one of the challenges. But we've got each of these 3 coils that are putting out these flux lines. And depending on how we control the currents in these, we can get these flux lines to move in a tremendously complicated paths. That's part of what our math is doing, is allowing us to predict what those paths are and then guiding these catheters so that they can get just exactly the kinds of bends we want. And I think that's, I like this video because I think it shows really the complexity and gives a sense of what's going on in our system and how it's able to do that. Just as easily, we could use this system now to start guiding micro robots if we, and we have started doing some of that, not just the catheters. And now you'll see a procedure that we do. We do a lot of simulations. So these are all physics-based simulations. Here's our patient. You'll see the mechanical advancer guiding the catheter into the femoral artery of the patient right here in the groin. And pretty soon you will see, as we go inside, what you'll see that at the tip is the guide wire. This is the sub-millimeter size device with a magnet at the tip, and that's that's kind of the leader. That's what the surgeon guides up deep into the. Here's going up one of the arteries into the brain, and as that guide wire, which is quite flexible, is moved up into there, then another catheter kind of follows it. And that's the catheter. In this case, if it were a ischemic stroke, which would have an aspiration, it would be able to suck it, or it might have a stent retriever and be able to deploy it to grab that particular device. And it can make, like I said, quite complex turns through complex anatomies and tortuous vessels. And then you just slide the basically the working catheter right over that, and that's how the procedure is typically done. So just show the final end of this. And now the guide wire would be taken out, and then the procedure would start of whether it's filling an aneurysm or removing a blood clot or something like that. Like I said, we spent a lot of time on modeling these. This is a physics-based model. We use an open source software framework out of France called SOFA for soft robotics. This is a full 3D simulation, but we're just showing it in a plane to show how it works. We've taken that complicated field, and we're just kind of showing just snapshots of little bits of the field. And now this is real on the right is an actual system, and this is the simulated system. You'll notice these three pieces on here are magnets, and there's a good reason in our design we like to have three magnets in there. It gives a certain stability and a certain dexterity to it, and we can feel that these are complicated simulations, but we can actually get quite accurate estimates of performance, which means they're also good for training surgeons. You don't need to go in with a real system. You can actually train in software to understand how the system works and to guide it through these complicated pathways here. We're doing a lot more than just treating stroke with this. I have people in the group that are looking at going across giant aneurysms, the cardiac ablation procedure. We have endoscopes, small 3-4 millimeter diameter endoscopes that we can move into the stomach to do gastric scanning. And more recently, we've been working with fetal surgeons on performing fetal surgery. And that video is not going, it seems like here. Let's see. It didn't go. Oh, well, I'll have to check that. No, here we go. So these are a number of different procedures, and so this is one of the student projects we have, master's projects, PhD students working on looking at other uses besides the neurovascular procedures for this, where our other team is working on doing the regulatory process and getting these across so that we can start using this in hospitals and patients and put it on the market. So that's what I wanted to talk about. I spent a lot of time talking about catheters and endoscopes, but what we're really known for and what our basic research, our fundamental research is on microrobots, robots that can swim through our blood vessels that are the size of red blood cells, and the challenges there are of course incredible and exciting. And it's not always obvious. A lot of the physics we use for catheters and for larger scale things don't work so well at small scales. And so when we started thinking about how to make microrobots swim and what the best way to do that is, we were inspired by bacteria. Bacteria, like flagellated bacteria like E. coli, are quite interesting because they in themselves are microrobots in a sense. They're a single cell. They're around a micron or two long, but they have sensors on them to sense their environment. They have a communication pathway that has an effect on how the motor that they have turns and rotates. And they also have software inside these DNA plasmids that are producing the parts that they basically telling what proteins to make so that they can make their motors and make their membranes and all that kind of stuff. Bacteria were first discovered and first reported in the 1670s, so several hundred years ago, where they were first seen. And when people looked at them, they thought they were swimming like a spermatozoa with a kind of traveling wave. When they first saw them, and everybody just kind of assumed that. But it wasn't until about 300 years later, when Howard Berg started looking at them when he was at the University of Colorado, that he realized they actually had a rotary motor. And that was quite astounding to learn. They had a rotary motor. Now, we don't have the nanotechnology to create that rotary motor. It's about 45 nanometers in diameter. But we do have nanotechnology that can create that flagella. And so that's something we happen to be working on at the time. People like Li Zhang at the Chinese University of Hong Kong now we were working with, and we realized we have flagella similar to those little propellers. And if we put a little magnet on the end of it and we rotated a field, that rotation should generate a propulsive force and cause our device to go forward, just like real bacteria that I showed in that previous video do. And we were able in 2007 to realize our first artificial bacteria flagella. And so we spent a lot of time over the years figuring out ways of making better ones. These were made with gallium arsenide and indium gallium arsenide and toxic materials, but they were just a first start. And then over the years, we started using direct laser writing, biocompatible polymers, as well as iron, which is relatively biocompatible. And we've learned a lot about how to fabricate them and how to functionalize them, and even how to use them to advertise our university for us. And we've even won a Guinness Book of World Records for them. And we've got them almost as small as a red blood cell. The big thing there is a human hair. The little device is our smallest ABF that we're interested in making, and that's a red blood cell. So we're able to make them reliably, consistently, and we continue working on the material sides of this, but also on the functionalization side. So one thing we also did was we took 80,000 of these, a swarm of these, 80,000. We tagged it with a near-infrared dye, and we injected it into the peritoneal cavity of a mouse. Here's that functional ABF swarm fluorescing through the skin of the mouse. And then we were able to drive them like a cloud through the mouse peritoneal cavity as a swarm. And so we build biodegradable ABFs and functionalize them with liposomes. We've shown DNA transfection. We've done a whole lot of stuff. If you look at our papers, we can talk more about that. But we became interested several years ago, almost 10 years ago, about how can we make them, those are pretty stiff, how can we make them soft? And so another parasite that inspired us is a parasite called Trypanosoma brucei that lives in the gut of a tsetse fly. And when it bites a human, that parasite can get transmitted into the blood of the human, cross the blood-brain barrier, and then it proliferates. It has creates a horrible disease in Africa called African sleeping sickness, or trypanosomiasis. But what interested us about this bacteria, or this parasite, was that it had several different morphologies in its life, during its life. And two of them that were interesting were a long, slender form that allowed it to swim, and a stumpy form where it could just sit there. And we thought, well, that would be pretty useful for a microrobot if it could swim at certain times and then just stay where it was told. And so Henwei Wang and Stefano Fusco and some of the folks with me developed a fabrication procedure with polymers and graphene flakes and magnetic particles that allowed us to expose our microrobot to infrared laser, heat it up to about 45 degrees centigrade, and move from this long, slender form to this stumpy form. One of the other things that was exciting about that was it also allowed us to experiment with a lot of different morphologies then, so we could start looking at testing out different geometries to optimize their shape and strategies and these kinds of things. And so that was quite interesting for us. One of the things I've always wanted to do, though, is make these autonomous, so they find their own. They find, we don't have to guide them. But the other thing I always wanted to be able to do is program them so that I could in situ create different behaviors, and we weren't sure how to do that. But then a couple of my Chunyun Wang, who was working here as a postdoc at the time, met up with another postdoc who was working with Laura Heiderman at the Paul Scher Institute here. And Laura is an expert on nanomagnetism. And Laura taught me something about magnetics, about small scale magnets that I never knew. And that was, I just knew they were super paramagnetic, or they were large and had multiple domains. So they were single domain or multiple domains. And they either, had no coercivity, or we could generate a high coercivity. But there is a scale in here of a few hundred nanometers where, depending on the size, we can tune the coercivity of our nanomagnets. And so if we can pattern using the same material, in this case, cobalt nickel, at different scales, we can actually have, with the same material, several different magnets, hard magnets, with different coercivities, different anisotropies. And so that put a lot of ideas in our head, like, oh, we could all of a sudden start patterning devices with these different magnets, and maybe there's a way then we could get them to magnetize differently and create a whole new class of deformable magnetic objects. And so what we ended up doing was, we took, the first system was pretty simple. We just had simple hinges these pads here with different patterns on them, these panels with different patterns and at different scale nanomagnets. And so then we would expose this to magnetic fields of varying strength. So we'd have a high field in this direction, and then we'd reverse the field in the other direction, smaller. So this side, this one would get, remember its magnetization, and then this one would get remagnetized. And then we could do this in another direction as well. And so with those four panels, we were able to generate 16 different magnetization configurations. And then with the same exact device, by just reprogramming it magnetically, we could get it to behave differently and when exposed to the same magnetic field. And so this is an oscillating field up and down, and we were able to show the same device, and you can see the scale bar there. It's just 10, 20 microns in size, get it to behave differently. And so when you get a couple of smart, ambitious young guys like Chu and Huang, they started thinking about taking the next step. And so they started thinking about origami cranes, because these are origami folding devices. And they thought, why don't we pattern the parts of this origami crane with different nanomagnets? And then what we could do is we could take those and we could reprogram the same origami crane to behave differently. And they were able to show 4 different behaviors with this. This is a kind of flapping behavior with a certain program, a magnetization program. And then they remagnetized it and got different behaviors. This is a kind of a turning maneuver it was able to make. Then they did a kind of a hovering behavior, and finally then a side slipping kind of behavior. So these are some of the creative things that they were able to do. Now again, these are with cobalt nickel. It's something nothing you probably want to put in your body, but it has it shows us paths forward and how we can encode different behaviors via magnetism in these. So sort of like, it's almost like storing storing data on a disk drive, right? On a magnetic disk drive, we can store the magnetization, then use that in a mechanical way, in a physical way. So showed you a lot of things so far. I want to kind of summarize what we've done at this point with our magnetic work. We still believe in electromagnetism as a good vehicle for medical robots. We know a lot about how to project magnetic fields in the body, how to control things with it, and also about the toxicity of the materials. Recently, we've realized nanomagnetism can allow some new kinds of behaviors to create programmable, reconfigurable devices. But we also realize there's so much more to do here, right? And even when I go back to the robotics part of this talk early on, and the kinematics and how we're looking at these fields, we've only touched the surface. We haven't really looked at the dynamics of these fields. There's so much more design work we can do there that's really quite interesting. And so I think it's a very rich research field and quite interesting for us to do. Coming back then to the medical robotics side, one thing we've seen in this field is success. We've seen hospitals wanting to use it, doctors demanding to use it. We have seen companies successful acquisitions, investors willing to invest in it. So we're still excited about it, but it takes a long time to get there. New ideas can take a couple decades before you see them get out, but you got to start somewhere. And it's interesting over the years what I've seen and how we see why is it taking so long, and why do we see failures in this field? Well, the first thing I think we always do is we underestimate how hard these things are. We underestimate complexity. That's the story of robotics, but it's also the story of a lot of new science and technology fields. We're often a hammer looking for a nail, and we're not sure what we want to do. The other thing over the years, as I've worked with doctors and hospitals, is understanding how critical it is to understand the surgical workflow. How is it hospitals work? How does their purchasing work? But how does it work in an operating room? How are new machines brought in? Where does the nurse stand? Where does the doctor stand? What are they used to doing? And how can we work within that workflow with them? The other thing in medicine is incremental change is good. You don't want a doctor coming in trying some new experimental procedures on you unless you don't have much hope. You want them to be very cautious in how they move forward. And so we have to have realistic views of how our technology is going to be adopted. And of course, if you want to kill somebody's paper with a paper review, you just put down, an incremental result. But in medicine, that's a good thing, right? And the other thing is understanding the business models and realizing how is it that investors see that they're going to be able to make money here, and what are they looking at, and what are what parts of the technology excite them from an investment and a business standpoint. I think that's important. And then finally, I've alluded to it a little bit. What we really want in this field, in what we're doing, is we want to improve healthcare worldwide. There's like 8 billion people in the world, almost 8 billion people. 5 billion people do not have access to safe, affordable surgical care. And a third of human disease, it's been estimated, is amenable to surgery. So we need to be able to provide surgery to many, many more people than we are. Will this technology do it? Because it's expensive. So the first thing is these systems the cost has to be reduced. And there are companies out there that are looking at lower cost systems and how they can make money that way. The other way that it can be a benefit is that these systems, instead of spending 7 years studying how to be an interventional neuroradiologist to push, pull, and turn catheters, you can come in our system and with much less training, all of a sudden, as long as you understand the anatomy and the medical condition, you can start being useful because there is a lack of neurosurgeons capable of doing these procedures. And the other thing I think is key is remote operation of these systems. I mentioned I was just down in Botswana last week, visiting a remote area, showing that we can control our medical robot devices from there back here. But what we really want to do is I want my expert radiologists here to be able to control devices down in the remote clinics in that part of the world. And we think that's one of the benefits of our technologies that I was showing you, because we're controlling the forces and torques on the tip of it, and able to get around that non-collocating sensor problem. So I think that gives us a lot of capabilities. We're excited about it, but there's a lot of work to do. And I'm excited to try to do this, try to get these into some of these remote areas, and try to develop smarter and smarter micro robots as well. So I want to thank you very much for your attention, and I'm happy to have some questions, and I guess we have a panel discussion and all that. So thank you very much.
Okay, great talk. Yeah, Brad, I was so excited for see so many new results, and a very exciting story for the medical robots and the navigation system. I see, 7 tons. That's wow, a big stuff, right? Yeah, not only just moving in, but how to educating the people to use that. It must be very difficult things. Yeah. So let me share okay, can you stop sharing? Okay. Okay, I share this one. Yeah. Okay, thanks for nice talk. Let's move to the panel discussion. I think many questions moving for you. Our panelists, the first one is Professor Mengdi Han, was Peking University. He's working in the biomedical department. It's a new department, but he's very interested in your stuff. And our next panelist is Professor Longqiu Liu, was from Harbin Institute of Technology. He's an expert in the micro and nano robots. He did a lot of nice work. I think this time he has a lot of questions for you. And our challenger today is Dr. Xu Ma Yue. He's from Imperial College London. Ma Yue was got PhD degree this year or last year, and now he is a postdoc in Imperial College too. And he is working a lot, I want to work a lot in bio stuff and micro nano robots. Okay, yeah, let's welcome everyone. Get on the stage, and as usual, we start from Ma Yue. Our challengers, Ma Yue. Turn on your microphone, please. Yeah. So please. You mute, Ma Yue. Okay, please.
Okay. Yeah, thank you for your introduction, and thank you for Professor's very excellent talk. So I think it's very impressive in both research side and also business side. So my question is, I'm like thinking the EMNS system is really very powerful. And my question is it possible to use this system to manipulate multiple robots to allow independent movement at the same time? So I think it would be a challenging task, but I think it also would be very interesting to say that maybe two robots, micro robots working together and cooperating with each other, so maybe can finish a very relatively complex task at the same time. Do you think it's possible?
Yeah, that's a really good point because this is with the fields you're generating one command to everything. It's not like you program each one individually. So there's a couple of strategies you could use. For micro robots, what we've demonstrated is we can generate different robots with different frequency responses. Okay. So if we have different, at one frequency, one of them will respond to the field and the other one won't. And so you can select a few that way. You can purposely make different robots with different properties so that some of them will respond and you just change it and do that. Of course, it's not like each one gets to do exactly what you want, but at least it's it's one way of doing it. So that's one. The other is with the catheters and the endoscopes. If we use a variable stiffness of material where we can, have it very soft, then it will respond, and then we stiffen it, and then we can let another one respond. Yeah. And so that's the trick we use there. But yeah, there's limits. I know we did some work many years ago where we were trying to figure out if we could generate very localized magnetic fields and gradients, and it's a real challenge. But I suggest people, if you're interested to go down this route, go look at the magnetic particle imaging people. They're active in Germany, and they have a way where they generate these super high gradients, and they get a zero field, and they can just tune a little piece of field. But man, those are hard systems to make, and they have very small workspaces right now. But there's some people working on it, so there's hope. But it's a hard problem. Yeah, thank you.
Yeah, thank you for your answer.
Did you have other questions, Manuel?
No, that's it.
Okay, great. Maybe I follow another questions with you. So Brad, I saw, the big stuff, when you generated the, magnetic field and, clusters was moving inside. I'm very curious about how you do the calibration due to the different patient or different, these kind of situations.
Yeah, that's a good, another key point. So there's two points of calibration. One is calibrating that matrix that goes from the currents to the fields and gradients you generate. And so what we have a calibration cube. Okay. And it's a 5 by 5 by 5. So it's got 125 3-degree of freedom Hall sensors in it. So those Hall sensors, we just set it in the middle of the workspace and we run through a sequence. And then we can develop models to do that. And so we've actually used some machine learning techniques as well to do that. So that's how we can calibrate that. Then there's the other calibration problem of getting everything aligned, positioned with the fluoroscope and all that. Now, the advantage we have is that you're always doing this under human guidance, under surgical guidance. Okay, so the surgeon can see how it's going, and he can or she can readjust. And so that's closing the feedback loop with human knowledge. And so then that's not such an issue for us. But calibration, yeah, always an issue with complicated systems. That's for sure. Yeah.
Okay, great. Not only artificial intelligence, also use the intelligence of a human to help.
Right. Yeah. I mean, you look at these, and the surgeons are always worried when they're going to get replaced by the robot, and I'm like, we're just trying to take the hard, we're good at certain things, but we're, the judgment and understanding the anatomy and seeing the way all this goes is far beyond anything we're going to learn or do automatically for quite a while, I think.
Yeah. Okay, great. So yeah, Mengdi and Long Chiu. Yeah, which one go first? Okay, Mengdi.
How many questions can I ask?
Okay, 2 or 3. Okay, just to save some time for Long Chiu.
I'll ask 2 long questions and 1 short question. So it's hi Brad, it's very amazing to see that you build many medical instruments that can control a catheter in the blood vessel. I assume you use magnetic materials in the catheter, and the magnetic materials might be permanent hard material. Right. Probably sometimes you need to program the direction of magnetization to be able to perform very complex motion modalities. My question is that for hard materials such as neodymium magnet, usually they are toxic, they are not biocompatible. So how to deal with this issue? For catheter application, probably you can just coat a layer of polymer or silicon dioxide, because the catheter only stay in the body for a very short of time, right? But for micro robots, if you use permanent magnet, they have to stay inside the body for a very long time. How to deal with the biocompatibility issue?
Yeah, I'm glad you asked that question, because I think a lot of people in the field ignore that question. And I think what the problem is then is that the things they're showing have no future, right? Because you can't leave something toxic in the body. You can't leave neodymium in the body. It's a well-known toxin. You can't leave cobalt. You're not going to get long, at least in large quantities in the body. But you're right. With catheters, we use neodymium magnets because they're the best we've got. We can coat them, and we know we pull them out. There's no danger of them staying in the bodies. That's easy. So what about micro robots that are going to stay in the body? Most people are looking at iron oxides, and of course that's a soft material, but you can still generate forces on it and torque, so you can still use it. And so there's a lot of folks, and I come back to Li Zhang, who we work on a project with in Hong Kong, who's doing swarms of these, and there's several other groups that you've seen things come out on as well. So we can use iron oxide, that's well known. But if you want to do a hard magnet and you want to leave it in the body, what are you going to do? Now, there was some interesting work in the last few years. We thought about iron platinum. We hadn't gone down that route, but Pierre Fischer, who's just moved to Heidelberg now, he's been working with iron platinum, and that has a pretty good coercivity. I'm still not sure how strong it is, and I still think there's some questions on how good of a permanent magnet is. But we watch that work very closely, and we're trying to see if iron platinum is an alloy that we can make a case for biocompatibility, biodegradability, and make it hard. Now, there's one other answer too, and if you can get these nanoparticles to be below 6 nanometers in size, then they'll be renally cleared. They'll come out in your urine, right? But I think that's a big challenge, and I don't think that's probably the right way to go. But if you could do that, you might be able to use something that's a little more nasty, maybe. Thanks.
Yeah, I see. I have another question. I think almost everyone who is doing micro robots know the science fiction Fantastic Voyage, right? And how far do you think are we? How long can we reach that goal? Like the movie shows that we have a very small machine that can go freely inside the blood vessel. What's the biggest issue? And do you think that's the ultimate goal of micro robots, or can we go beyond that idea?
Yeah, I mean, I if we could do Fantastic Voyage, I'd be happy, and I'll call my career finished. Then I'll retire. So I do think what we will see, and I don't think it's going to be that long, that some years away, certainly a few years away, 3, 5, 8 years away, we're going to see devices that are steered within the blood vessels, that are moved to locations to help dissolve a blood clot in the brain. I think we're going to see that. I think people are starting to understand what the material issues are. We're starting to see what the fields that we can generate are. That's relatively simple to do, but it's still very, very important, because like I showed you, stroke is the second leading cause of death in the world. And if we can target these blockages in the brain more easily, then I think that's important. The other thing is when I talk to neurosurgeons, they say, there's a lot of blockages in the really small blood vessels that they don't know what to do. They don't think they can get to them, and they're not even sure what the effect is. But they said, if we had ways to go even smaller, we think that you basically can clear out your blood vessels in your brain and restore blood vessels. Maybe there's a way we can do that. So, in the future, when you get to be older like me, you may go to your doctor and they say, we're gonna clean out your brain, right? And they inject some micro robots in, and they start just letting them go through and kind of dissolve some of the plaque. And maybe that's a future that's kind of crazy. But I think in the near term, we're going to see larger blockages that can be treated that way. There are some startups out there. There are companies that have gotten funding. There's one, Bionaut, out of Los Angeles. I think they've raised 20 million. they're looking at devices that can go and treat glioblastomas in these very aggressive brain cancers. So they've got investors that believe in that and are going down that path. So I think there's some interesting possibilities there. But the future, I think as we get more complicated electronics, we understand the biocompatibility issues. I mean, let your imagination run. That's for the younger people to come up with some of those crazy ideas, I think. So.
Yeah, I see. I believe that in the future we can realize those crazy ideas.
Yeah.
And the last question is very short. I noticed that you have the title of your talk has nano robots, but maybe you didn't talk about nano robots a lot in this talk. So my question is, what's the difference between nano robots and pharmaceuticals, in your opinion? I think they are quite similar.
Yeah, I mean, I'm not as comfortable with the word nanorobot as I used to be. People like to say nanorobots, and I think anything that's small that you can make move, you could say, oh, it's got some robotic capability. So if you can guide its motion in a way, I would say, oh, that's a nanorobot. But to me, what becomes less interesting is when you get to be around a few microns or less in size, then the motion becomes dominated by Brownian motion. And so then it's not quite so interesting to me because it's harder to control. It's much more random. And so I don't talk about nanorobots so much. I put it in the title because people like to hear it. But I have a chemist, Salvador Pani, and he's interested in things like MOFs and multiferroics and these things and what they can do. And I think that's really more on the nano scale. I teach microrobotics here, and he teaches nanorobotics at ETH, and he really gets more into the chemistry of it. So yeah, good point.
I see.
Yeah, okay, I think his class maybe have more students. Okay, Lo Qiu, hi, please.
Yeah, hi, Brian.
Hello.
Yeah. So it's a very nice talk. It's very impressive for me. Even I have learned a lot from your papers, and also I read a lot of work that you have done. So I have a couple of questions. So for the first question, so compared with the commercial catheter, for right now, there are also some of the catheters to be used to treat the people, right? So as you mentioned, for this kind of nice magnetic navigation system for this kind of new catheter, I'm just wondering, what's the big difference between these two? Because for the current catheter, they can also control the direction, and they can also navigate to a specific object. And I'm not sure what's the big difference that or what's the big advantage for such of this kind of system.
Yeah. I think you're right. There are other companies out there that have other approaches. So there's a company, RoboCath or Arcath, right? And then Corindus. No, it's RoboCath and Corindus. Corindus was bought by Siemens a little while ago. RoboCath, I think they're active actually in China, if I'm not mistaken. They've got some. I mean, they're actually out of France, but I think they have some things there. What those two systems do is they just basically duplicate what the radiologist, the interventional radiologist is now, which is push, pull, and twist at the back of it. They're not controlling the tip. So that makes actually the control problem a challenge. And I mentioned that the non-collocating problem. Because you're trying to control the tip of something, but you're controlling it from way back here. And that means it's very hard to do that dexterously. But there are some of the advantages of their systems are that the surgeons then don't have to stand next to the patient and get the X-ray radiation so that it saves them. But they're really not improving the dexterity. In fact, I think they're probably not quite as good as the traditional way that it's done, because people just haven't had as much experience. Maybe eventually they'll get there. So those two companies are just doing it the old way. They're not controlling the tip, unlike us. Now there are a few other companies out there, companies like Bendit, And they have a catheter where they can control the tip. They can kind of unroll the tip and get it to just bend in one direction. So you push it in, you can twist it and bend it in another direction. And I think those companies, I certainly watch out for them because they're going to provide some advantages. You're not going to be able to have to replace catheters so often with different bending. You're going to be able to do that. I think that's interesting. But I think, of course, I believe in our technology. That's why I'm doing it. But I think our technology gives you more capabilities, more ability to change the direction of the tip and move it in other directions and actually apply it. And you're still not relying on that rotation from the back to move it into location. So there is, if you look at the real kinematics of what you're doing, our system, well, it has the complicated magnetic system to it. The actual motion is actually much simpler. And I think that's where the win will come. But our system, the downfall is our system, you still have to get the capital equipment. You have to get the big system in there and you get it in, whereas theirs is an easier system to go. So I think we need to do more head-to-head comparisons of the two, and probably in the end, maybe a combination of both might make the most sense. But there's competition because there are not enough people being treated for stroke. There's a greater need. A lot of folks can use treatment that aren't getting it. There are not enough doctors that can do the procedures. And the insurance companies are willing to pay a lot of money for these procedures because if you suffer a stroke, it's very expensive socially. You've got to this person is going to have disabilities and they're going to have to be taken care of by society. So, there's a lot of motivation to solve this problem and to spend money to solve the problem.
Okay, maybe I follow this
question. Thank you.
Lochio, I have another question just to follow this. Okay. Yeah. Sorry for this trouble you. So Brad, so do you see your procedure is kind of more, I think it's more flexible, right? Yeah. It's more gentle, maybe, can compare with all other, kind of standards. Another thing is that possible, you have this magnetic, you have these structures. It also can be functioned, to be one part of the surgery.
To functionalize the tip more, you're saying to functionalize the tip. Yeah, that is possible. So I know there's a company out there that, for instance, they have a little sensor they've developed that's not on the market yet, but they're putting it in there in the tip. And so when they go and they touch the blockage, the blood clot, they can sense some properties of it. And that will tell them what's the best way to remove it, because you've got basically two ways to remove it. You either suck it in through a vacuum, or you put this kind of cage stent retriever on it and you pull it out. And that one works better depending on whether it's a more solid or a more liquidy kind of thrombus. And so that's one thing people are doing, is looking at that. I think it would be cool to put, we've got little cameras now that you can get from OmniVision that are 600 microns or so on a side. Wouldn't it be cool to have little cameras in these things and be able to show the doctor, for the doctor to see exactly what, in there, rather than just looking at the x-rays. And then, pressures, you can imagine a lot of things that would be good to measure that the, micro nanosystems community would be able to bring to bear on the problem.
Yes, great. Okay, sorry, Longtail, please go ahead.
Yeah, so there's a lot of questions that, for the vessel, it's blood vessel is really tiny or really small, especially for some of the tiny one. So I'm just wondering, once it gets stuck for this kind of magnetic, system, how could we take it out, or how could we just pull it out, or how could we just control it? Or will it be harmful for our vessel as well?
So for catheters and guide wires, you're going to pull it out, and that's one of the tests to get them to put them through the regulatory process to get approved for medical device use. You have to do tests on how much force it can withstand before it breaks. So that's something for a catheter guide wire you need to know, and it's important to have that controlled in the manufacturing process to make sure that it's not going to get stuck or break off. For the small micro nano robots that are untethered, they have to be biodegradable. I think that's a key. You have to use polymers and magnetic particles that will degrade over time, so that if they do get lost, it's not going to cause a problem.
So, because for instance, once you get some people get have a stroke. So once it gets stuck in the stroke, so that people will more serious compared to the previous one, right?
That's right. Yeah, yeah. You don't want to make the situation worse. That's for sure. So yeah, yeah.
Yeah. So the last question that I want to wonder is, so for your system, I remember, so one of the system you had to use like 7 tons for the for this one, and you can generate like a magnetic field like a 130 millimeter, right?
Yeah,
so
yeah. You're right.
I'm just
you know
wondering,
the numbers,
for such
yeah.
a strong, for such a strong magnetic field, is it harmful for the people's healthy, or is it still okay?
No, the fields are relatively, so that we're looking at, like you said, 130 millitesla. MR, people are put in typically 1.5 Tesla, 3 Tesla. Even I think regulatory lets you go up to 7 Tesla. These are super strong fields. So the fields aren't the problem. The thing people are more concerned about is the frequency, because you can heat up, you can cause some issues if it's a high frequency, but we're not even close to those frequencies. So we have no problems. And in terms of gradients, I don't think there's any standards. I don't think it matters what the gradient is that I know of anyway, because it's the field and it's the frequency that the field changes that you need to be concerned about.
All right, thank you. Okay, so that's all. That's all my questions. Thank you very much.
Okay, it's my turn. Okay. So, Brad, there were one question from the audience was Ray. Yeah, thank you, Professor Brad Nielsen. This is an impressive talk. The catheter robots have come a long way in terms of actuation, but current, the robots lack the sensing capabilities. His question is how to develop a more intelligent catheter robot, and what about off-board sensing, just like off-board actuation?
Yeah. Great question. Force sensors would be nice that can measure this. And so I talked about cardiac ablation, where you put a catheter into the heart, and then you basically you get a good contact with the heart wall at a particular location, and then you use a radio frequency signal to kind of basically ablate a little piece of the heart. What's important there is getting a good contact with the catheter on the heart wall, and that force is important. So there's a company, Endosense, I think it came out of Lausanne, that was bought by St. Jude Medical, and they have an optical sensor that can measure that force. And I know a lot of electrophysiologists who do this like that. They like to know the force. It gives them more confidence that they're getting a good contact. So I think force sensing is important. I think probably local mechanical properties are important to know. And then, is there a way you can use, your fluoroscopy, your X-ray imaging to sense something? I don't know anybody doing that, but maybe there's a way you could somehow coat your catheter with the material and then sense a change in the X-ray reflectance or transmission, and maybe you can make a measurement there. I don't know if anybody's doing that, but I guess it's something to think about. But yeah, we always want more sensors, and maybe. But the other thing you got to worry about though is cost, because it's a very cost sensitive procedure, and you want these to be disposable devices. You don't want to have to sterilize them, and so you got to think about how you can make your devices easily manufactured, and that's another part of the question. So.
Okay, super. Actually, it reminds me Mengdi. Mengdi a few years ago, published a paper was with, temperature sensing, right, Mengdi?
Mm-hmm.
Yeah.
Okay.
And in your paper?
We integrate electrode with temperature sensor and also tactile sensor or pressure sensor, so that when we are doing cardiac ablation, we know the temperature increase when we are doing the radio frequency ablation. And we also have pressure or tactile sensors, so that we know the contact between the electrode and the cardiac tissue. And we published a paper in Nature BME in 2020, and we just integrate arrays of electrodes, temperature sensors, and pressure sensors on the balloon catheter, so that when the balloon is deflated, we can insert it minimally invasively, and then we inflate the balloon so that the devices can contact with the cardiac tissue, and we can do ablation. We can measure the temperature and the pressure. So that's basically our work.
Oh, that's great. Yeah, that's super important to have that kind of information, I think. So good.
Yeah, I think this this can be used for the sensing part. Yeah, if integrate the sensing and actuation together, it will be more powerful. Yeah. Okay, Brad, I have another question for you. Is you have a 3 company, right? Your technology spin off of a 3 company. Yeah, all these 3 companies were successful. Yeah.
It's been, so here's my advice. Don't actually we have spun off, I think, 7 companies out of this group at some point. I don't advise anybody to do that. The first company we spun off is a company called Femto Tools in 2007. And it's not biomedical. It makes force sensors. We had developed back in the late 90s when I was at the University of Minnesota, and they're doing well. They're a company with about 25 people, and they work a lot in material testing and testing things like wafers and small devices. And so, that's a company that's been out there a while. I used to be more involved when it was starting, but then it's kind of being run by a very competent CEO and CTO. So, and then we founded a company, Aeon Scientific, in 2010, and we actually had an angel investor for that, who used to be the chairman of Sandoz, a big pharmaceutical here, and he was the chairman and the angel investor, and he was just ready to put in a whole nother investment round. And unfortunately, he died of a heart attack and had owned 50% of the company. And so we tried to keep that going, but it was just with the ownership and everything. What we were able to do then was take some of those assets and patents, and we spun off this other company called Magnabotics. We'd already done that before, and we just brought that there. And so Magnabotics is a very small company, but it produces some of our magnetic navigation systems and some of those patents. And so that's been useful. And then we just founded last November Nanoflex Robotics. And so that's a company with about 15 people now, some investment, and their job is just to take some of these things I've showed you and move them through the regulatory process and do some clinical trials. And so that's what they're focused on right now. I've learned a lot from the companies. I have not gotten rich, and I don't think I will, probably until after I'm dead, to be honest. So, so maybe my kids can enjoy it, right? But that's not why I did it, right? The reason to do it is it's a challenge, and as engineers, there's nothing more gratifying than to see your work actually out there helping society. I mean, one of the most thrilling points of my career was sitting in the operating room and watching the patients be treated with ablation catheters, and know that system, the ideas and everything started with my group. And that was one of the highlights of my career. And
yeah, it is very great. Yeah. So actually, if encouraging the people, to get to their own startup, but they will be encouraged. Yeah, because
it's
everyone
hard work.
like that had a feeling.
It's hard work, but the most important thing is a team, getting a good team, right? Your team, getting the right people to work with that make it fun to work with and that are very competent. The second thing is the technology. You want some good technology, but without a good team, I think it's not going to be fun. So you want to make sure you surround yourself with the kind of people you want to work with. I think that's quite important.
Well, you should be very proud. But like you say that when you see the patient, all the ideas can help him. That's very important. You can really help the people. I think that's, CT Lim was from Singapore, National Singapore University. He once said a word. He said that once you are engineering, the most important or product part is, you just make only for yourself. You make these tools can save, maybe 100 people or millions of people. That's a more important job for engineering people.
Yeah. And you're going to be remembered for that more than for how much money you made, right? So that's good.
Of course, we're excited, for how many people we save. Yeah. Okay, Brad, the last question is for you. I know you have a colorful life, right? you have the experience in Army, you have experience to be, professor, you have you involved to start up the companies, you also have a very active to help others, in this kind of, different projects. So how you manage your time?
Well, I have a great team, here at ETH. I have a great support staff. I have a lot of assistants, like for my editorial duties and those things. I have people helping me. And I have a very supporting wife who's willing to put up with me, she's used to it, I mean, as professors, I used to tell her during my PhD, oh, just when I finish my PhD, then everything is going to be fine. And then it's like, well, I just need to get a position, then it's going to be fine. And I just need to get tenure. And by that time, she's like, you're just always going to work. So, and it's true, we just, the more you do, the more you want to do. And I think right now the challenge is trying to get the technology out, but we still get excited by the ideas, right? We still get excited by new, clever ideas and students that come in with new things. And, and I love it when a student has an idea and I'm like, I wouldn't have thought of that. I love that. So it's good.
Yeah, you already answered the question that I want to ask, how you always come out with so many exciting ideas, because you're exciting, right? You're looking for that, and you discuss with your students, yeah, always like a brainstorming, get out a lot of ideas, yeah. Very exciting, yeah. Cool. Okay, Brad, time fly. Yeah, I really want to, enjoy more talk, more discussion with you. But almost time we should stop. So it's my great honor and pleasure to, deliver this certification to you. So, our ICANX is a long-term, science online talk every Friday. We share the latest results of science and technology. We want to use this connect the world and the universe. So, Brad, we're proud of you. That's yours.
It's great seeing you, Alice, and I hope to get to China sometime soon and get back and see all my old friends.
You will come to Hong Kong next week, right? Yeah,
I'm going to be there.
Chance is here. Okay.
That's right.
Yeah,
right.
Going to see you in the near future. And next week will be our national holiday. So we also will host the, ICANX talk on Friday. Will be a special issue is for the Huazhong University of Science and Technology, the 70 years anniversary. So we will have a big team next week, and we will have a more fun, to enjoy all these alumni from different parts of the world. Some are very nice talk and very nice discussions. Looking forward to see you next week online, and that's ICANX Talks Weekend waiting for you every Friday. Okay. Okay, great. So cool, Brad, really, really great talk.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的